Hello everyone, I welcome you all in today's session. As we have discussed the concept of vector space in the last session, so let's see some examples in today's video. As we have discussed already the notations of the sets, जैसे हम Q define कर रहे हैं. Q is the set of the rational numbers. R is the set of real numbers. Similarly, C set of complex numbers. Similarly, M, N or R set of all n cross n matrices whose entries are from the set of real number. Similarly, P, N or R set of all polynomials whose degree is less than or equal to n. And as I already told you in the previous video that in your syllabus the field which we are considering are Q, R or C in your syllabus. Okay, so now in a vector space what we have, in a vector space we have a set V about which we have to show some properties, axioms. A set F, that is the field which will be either Q, R or C. The two operations, star 1 a vector addition, star 2 the scalar multiplication. Now we will take one example here. We will take example V as a Q set of rational numbers and a field F is Q. We will show that V, or in this way, Q over the set of rational number as a field with usual addition and usual multiplication is a vector space. For that we have to take the vector addition properties. So the first property which we have to see is here, that if you will take the any two rational numbers from Q, then with respect to the first operation plus, if you will add it a plus b, you know the sum of the two rational number is again a natural number. For example, if a is equal to p by q, b is equal to r by s, then p by q plus r by s will be equal to ps plus rq divided by qs, and here q is not equal to 0, s is not equal to 0, implies qs is not equal to 0. Now the second property, since q is a field, so it will be abelian with respect to the addition. So if you will take a, b and c are the three rational numbers, then you know a plus b plus c is equal to a plus b plus c. That's associative. Following by this, we have the third property. There should be some real number which will you add to some real number a, you will get the same real number a, that you know that is 0, and 0 is a rational number, so that is 0 plus a. So I can say there exists just one element 0 in the Q, that is here, and this is called the 0 of the vector. 0 of the vector, or you call it as identity element. Okay, then the fourth property, that there should be some element in A. If you will add to get the same identity element of 0 or the 0 of the vector, that will be minus times that rational number. So there exists minus A from the rational number such that A plus minus A is equal to 0, that is minus A plus A is equal to 0. And the fifth property, that is the commutative property. If A and B are the two rational numbers, then A plus B is equal to B plus A. So this is about the vector addition. Okay, so this is here V is equal to Q and your F is also equal to Q. So you have the two operation plus and multiplication. When we are doing the internal composition, so we are using the addition, and when we are using the external composition, so we are using the multiplication. For the internal composition, that's the vector addition, we have checked all the five properties, that it is an abelian group under the first operation, that is usual addition here. So the sixth property, which we are calling as the external composition or scalar multiplication. Okay, scalar multiplication, as we have already discussed, that the elements of the field is called the scalars. Okay, and the elements of this V are called the vectors when it is a vector space. So let's take any element from the field, here it is Q. Okay, and take any element A from the Q, because this V is Q, so here it is a V, here it is the F. So alpha times, because second operation is our multiplication usual, so alpha times any A is equal to alpha of A. Multiplication of two real number is again rational number is again a rational number. For example, alpha will be P by Q and A will be R by S, so it will be PR divided by QS. Okay, so that is alpha A. Then the seventh property is that if alpha, beta are the two rational number, A is again a rational number, that's our V, then alpha times, okay, or alpha plus beta times A should be, that is, it is again a rational number, so that is alpha times A plus beta times A. Okay, so similarly, eighth property, if alpha and beta are the real rational number, alpha is a rational number, A and B are the two rational numbers, then alpha times A plus B will be equal to alpha times A plus alpha times B. Why we are writing these? Because Q is a field, so it satisfies these properties. This is again a rational number, this is again a rational number. Okay, ninth, if alpha and beta are the two rational numbers, A is any rational number, then alpha times beta times A will be alpha times beta times A, or you can just change it because it is commutative, so beta times alpha times A. So similarly, the 10th property is that is there any rational number, if you will multiply it with any rational number, you will get the same, that is our 1. So the unit is here, unit is that 1 is in the Q, so it means that Q over Q with usual addition, usual multiplication is a vector space. Okay, so let's take one another example. If you will take Q over R, you have to check with usual addition, usual multiplication, whether it is a vector space or not. What will you do? You have to use all the above properties and you will check whether it satisfies or not. So in the vector addition here, before going through the vector addition, what is our V? That is the set of rational number. What is our field? That is the set of real number. So now take any two, with respect to Q, Q with the addition is a abelian group, so that means vector addition satisfies. So in short, I am writing it because we have proved all the q with respect to the addition, all the properties here. Okay, so now we will go directly to the scalar multiplication. Scalar multiplication. So for that, the first property is that take any element from the field. So alpha is any real number, a is any vector from the q, alpha times the second operation should be again in q. So is this true? For example, if alpha is equal to root 2, if a is equal to 1, so root 2 times 1 is equal to root 2, because root 2 is a real number, so we have to take a real number here, so it is not in the q. It means that it is not satisfying the scalar multiplication, so that means q over r is not a vector space. Okay, so in short, if you have any v any set and you have any field k, we say if. Okay, so if you have any set v, any set k, you have the two operations star 1 star 2. So if k is the superset of v, if k is larger than the v, then v over k with the first operation, the second operation is not a vector space, so it is the extra information, but usually check with the axioms so you can use this result. If k is the superset of v, then we say that it is not a vector space v over k. Okay, so here for example r contains the q, so that's why q over r is not a vector space. Okay, for example, we will take another example here. R over R, R over R with the addition, with the multiplication is a vector space. So let's say the vector addition. The vector addition. So field is our R and V is our R. Actually, you have to remember that if you have the field F and then F over F is always a vector space, is always a vector space. Even Fn over F is always a vector space. But you have to remember it should be the field. You know F is a field, then R over R will be a vector space. Let's prove this. So take the first operation here. Take the two vectors that's from R. So A and B are the two real numbers. Take the first operation, A plus B. Sum of two real numbers is again a real number. Second, a real number is actually abelian under the addition, so it should be associative, which we have seen already in the first lecture. Third, there should be a real number in R such that if you will add it with any real number, you will get the same. You know 0. 0 is a real number, that is 0 plus A. Fourth, there should be any element in the R such that if you will add it with any element, you will get the 0. So that is minus A. Minus A is a real number, so you can write it minus A plus A. You know sum of the two real number A plus B is equal to B plus A, so it means real number is committed to another addition. Now we will go through the scalar multiplication. Scalar multiplication. So take any element from the F. Your F is R, so take any R and take any element from the V. So A is any element, so alpha is real number, A is real number. Take the second operation, so that's multiplication of the two real numbers is again a real number. Second, take any real number alpha, take any real number beta from the R, take any vector from the R, then alpha plus beta times A should be alpha A plus beta A, because it is distributive, because R is a field. Okay, take alpha from the R. Okay, take the two vectors A and B from the R, so it will be alpha times A plus B should be alpha A plus alpha B. It is distributive, as I told you, it is the field. So now alpha beta from the R, A is from the R, then alpha beta over A will be alpha beta of A will be equal to beta alpha of A, and there should be one element from the R such that if A times that element should be A, so this should be from R, you know that is 1, so the unit is 1 here, so it implies that R over R with usual addition, usual multiplication is a vector space. Is a vector space. Okay. Similarly, you can find another one, that is R2 over R is a, with usual addition, usual multiplication is a vector space. Okay, so what you have to understood here, V is your R2 and F is your R. So understand what is R2. So R2 is a set whose elements are in the form of x1. So for example, if x is any element here, so it has the two coordinates x1, x2. x1, x2 will be in the R, is it? So this is the structure of this R2. Okay. So what you have to do, vector addition. Okay, now if you have the two elements, if x and y are the two elements from R2, it means x has the coordinate x1, x2, y has a coordinate y1, y2. So x plus y is defined in this way, x1 plus x2, we are x1 plus y1, we are using the first coordinate here and then the second, x2 plus y2. Okay, corresponding coordinates. Similarly, if you have any element, any real number a, you will multiply with it x. It means that a times x1, x2. So that means a of x1, a of x2. So here you are using scalar multiply in this way. So this is a defined operations how you can do it. So now we will have to check all the operations together. So this is how the structure of R2 is, how we are adding the two vectors, how we are using the scalar multiplication. Let's go now the vector addition properties. Vector addition properties. So that's internal composition. In the internal composition, we are using the first operation, that's plus. So take the two vectors from, what is our V? R2. So x and y is an R2. So now x plus y means x1, x2 plus y1, y2, because x is x1, x2, y is y1, y2. You will get x1 plus y1, x2 plus y2. You can check it is again the in R2 because you are getting the two coordinates, so it is in R2. Okay. Now the second, if x is equal to x1, x2, y is equal to y1, y2, z is equal to z1, z2, then x plus y plus z will be x1 comma x2 plus y1 comma y2 plus z1 comma z2. It will be equal to x1 plus y1, x2 plus y2 plus z1 comma z2. It will be x1 plus y1 plus z1, x2 plus y2 plus z2. You can see now x plus y plus z. Similarly, it will be x1 comma x2, and the addition of these two will be y1 plus z1, y2 plus z2. If you will add the first two coordinates, so it will be x1, so first coordinate with the first coordinate, x1 plus y1 plus z1, and x2 with this one, so x2 plus y2 plus z2. You will check the both are same. Okay, so it means that x plus y plus z is equal to x plus y plus z. Okay, so this you have seen the associative. Now the third property, what you have, that if you have any element in the R2 such that if you will add it with any element of the R2, you will get the same. So x is x1 comma x2, you have to add some element in from the R2, it should be again x1 comma x2. You know that will be 0 comma 0, and 0 comma 0 is in the R2, is it? So this is your R2, so this is your 0 comma 0. Okay, So this is 0. We are calling it as a 0 vector. Okay. So what is the fourth property? There should be one element from your R2 such that if you will add with the x, you will get the same 0. So that is x1 comma x2. You have to add some another element from R2 that will be 0 comma 0 because your 0 is 0 comma. So what will be that element? Minus x1 minus x2. So that will be, if x is equal to x1 x2, then minus x will be minus x1 minus x2. So we can say x plus minus x. So minus x, you can check, minus x is also the element of R2, so it is minus x. So the fourth property. Fifth property, x plus y is equal to x1 plus y1, x2 plus y2. Since this is a real numbers are commutative, you can write y1 plus x1, y2 plus x2, so that is y plus x. So now scalar multiplication. In the scalar multiplication, you have to take any element of the field. What is your field? Your field is R, because we have R2 over R. So this is our field F and this is our V. Okay, this is our V. First operation is addition, second is multiplication. So this is our external composition. So we are in external, so we will use a multiplication. Take any element of R. Let's say A is, or alpha is any real number, and x is any element in R2, then alpha times x will be alpha times x1 x2, that we have defined it already. Alpha x1 alpha x2, it is again in the R2. Okay, seventh property, take the two elements alpha and beta are the two real number. X is any element in R2, then alpha plus beta times x1 x2 will be equal to alpha plus beta times x1, because this is the sum of two real number, is a real number, so it will go multiply with each of the coordinates. So alpha plus beta of x2, so it will be equal to alpha x1 plus beta x1 comma alpha x2 plus beta of x2. It will be equal to alpha x1 plus alpha x2 comma alpha x2 plus beta x1 comma beta x2. So it is alpha x1 comma x2 plus beta x1 comma x2. x1 x2 is your x, so it is alpha x plus beta x. Okay. So similarly, now take eighth property. Take the two alpha is any real number and x and y are the two from R2. So alpha times x plus y, you have to check. So that is alpha times x plus y is x1 plus y1 comma x2 plus y2, because these are x is equal to x1 x2, y is equal to y1 y2, so the add will be this. So it will be alpha times x1 plus y1 multiplication with the first coordinate, similarly with the second coordinate. So alpha x2 plus y2, it will be alpha x1 plus alpha y1, okay, comma alpha x2 plus alpha y2. So that is alpha x1 comma alpha x2 plus alpha y1 comma alpha y2. So that is alpha x1 comma x2 plus alpha y1 comma y2, that is alpha x plus alpha y. Okay, so the ninth property is that alpha times x, alpha times beta into x. Okay, so that is alpha beta into x1 comma x2. So that is alpha beta x1 comma alpha beta x2. x1 is a real number, alpha is a real number, beta is a real number. So you can take alpha beta of x1 comma beta of x2. So you can say alpha beta of x. Similarly for that one. 10th property, is there any element from the field, our field is R, such that that element multiply by your x should be equal to x. So that means that element multiply by x1, x2 should be your x. You know that multiply will go multiply with x1 and x2, that is 1 only, isn't? So this is our 1. 1 is a real number, so it means that r2 over r is a, with usual addition, multiplication satisfies all the properties, so it is a vector space. Okay, thank you very much. We will check other examples in the next class. Thank you.